And perhaps fairly key to the process is the assurance activities that sat alongside this development process. I've already said that correctness by construction, the aim is to take small steps, check those steps to make sure that you're in the right place at each point, and to do all checking as soon as we can. So try and remove any errors as early as possible. And in order to do this, we performed a number of proof activities as we went along the development process. So we proved that the security properties held of the formal design, of the formal specification. We also proved a number of soundness properties of the formal specification. For instance, we proved that there really was an initial state. You could start this system. And things like the various operations described in the formal specification had appropriate preconditions. Then moving down, we performed static analysis on the software. We did all our static analysis in terms of things like data flow and information flow analysis and checking for absence of runtime errors before the code was reviewed and before it was compiled. So why should we formalize? Well, by using a formal notation for our specification and design documents, we've produced unambiguous documents which we can take to the client and discuss with them and be sure that both sides, both parties have a clear understanding of what's required. The specification was demonstrably complete, so we could tell that we'd cover every possible case, and it was amenable to formal verification. In our case, we used formal notation for the specifications, security properties, and the formal design, and all of those were written using the Z notation. And by choosing the Z notation, we were able to use the fuzz type checker for very quick type checking of the specifications. And by choosing a common notation, we were able to perform proofs of various relationships between the documents. So it was quite important to us to be able to prove that the security properties held of the formal specification. And we were also able to prove that the formal design was a refinement of the formal specification. So why did we use Spark? Well, again, it's a formally defined, unambiguous language. The code can be statically analysed early, so we get early indications that we're doing the right thing. And all the flow properties are very visible and checkable. And we're able to demonstrate the absence of many potential runtime errors. We also use Spark as a proof language, so we introduced proof annotations. And by using Spark as our proof language, we were able to use the enhanced dialect of Ada, which is easy to read by an Ada programmer. And we were able to choose the amount of our proof of correctness we did. We only did partial proof, and we only actually proved that the security properties held rather than proving full behavioural conformance to the design documents. And of course the Spark language is very well tool supported. So if we quickly look at the development statistics, well, we produced about 10,000 lines of code in the core software and a further 16,500 lines of annotations. Looking at the coding rate for the coding portion of the project, it's interesting to note that the core software, we got a much better coding rate than the support software. And this is down to the fact that the formal design was very precise. We had very little choice as to what to do in the code. We knew exactly what we were meant to be writing. The support software, although it was documented, the requirements were perhaps less rigorous and more questions had to be asked at the point of coding. And if we look at the overall coding rate for the whole project, well, the core software worked out at 38 lines of code per day. The project took 260 man days. There were 3 of us working on it, and we took 9 months elapsed. If we quickly look at some of the metrics for the project. This is a graphic which indicates where defects were found and where they were introduced. So for instance, here we have an 11 here, which indicates that 11 defects were found while we were coding in the informed design. And the C/C principle is we try and find our faults as soon as we can. So we want to be detecting things early, so on the right-hand side of the diagram, left-hand side to you, sorry. So anything detected up this end is a problem in our process. And we found 54 defects, and we felt that 8 of them were found late. And that was partly due to what we feel were probably inadequacies in what we'd done at the requirements stage. So, post-delivery defects. Well, the software was sent out for independent test as part of the contract, and that testing found no defects in the software. Between 2004 and 2008, the NSA had the software and used it on a number of research projects, and they still found no faults. However, in preparing for public release, we did find a fault. And since public release, we've had one further fault reported to us. So the fault that we found prior to delivery was, rather embarrassingly, a potential overflow of an integer type. Raw duration is an integer read from file, and in part of our type conversion, we used a multiply on that raw integer, so we could quite easily exceed integer last. This is detected using the EXP option with the Spark Examiner, and indeed that's how it was found. Unfortunately, I have to admit that the project used the RTC option, and it's a bit lost in the mist of time as to why we chose that option at the time. But it's interesting to note that this fault wasn't found during any test or use, and that's probably because the valid values for this input data are in the range 0 to 200, whereas the problem values are the order of 10 to the 9. So picking up on that particular test value is not necessarily intuitive.